Please subscribe to support the channel. Far beyond the reach of our sun's warm glow lies a colossal star that defies imagination, a true behemoth of the cosmos known as VV Cephei A. Hidden within the constellation Cepheus, roughly 5,000 light-years from Earth, this red supergiant is so immense that if it replaced our sun, its surface would stretch past the orbit of Saturn, engulfing every planet we know. It blazes as one of the largest stars ever discovered, a fiery monument to the universe's scale and mystery. VV Cephei A isn't just a star, it's a living furnace of unimaginable size, a dying giant nearing the end of its stellar life, reminding us how small we truly are in a cosmos that never ceases to astonish. VV Cephei A is a star that exists on a scale so enormous that it stretches the boundaries of human comprehension, yet it remains a tangible part of our universe, observable and measurable from our tiny vantage point on Earth. Classified as a red supergiant, VV Cephei A is among the largest types of stars known, occupying a critical place in our understanding of stellar evolution. Its position in the northern constellation of Cepheus makes it a fascinating object for both amateur stargazers and professional astronomers. Yet its faint appearance in the night sky belies the monumental proportions it actually possesses. Located approximately 5,000 light-years away, the light we see from VV Cephei A today began its journey before humans had developed modern astronomy, carrying with it a story of immense heat, pressure, and luminosity that we are only beginning to fully comprehend. Despite this vast distance, astronomers can detect its presence and characteristics through a combination of telescopic observation, spectroscopy, and light analysis, piecing together details that allow us to imagine its true magnitude. As a red supergiant, VV Cephei A represents a late stage in the life cycle of massive stars. Red supergiants are known for their enormous radii, relatively cool surface temperatures, and distinctive red hue, all of which are characteristics that define VV Cephei A. Unlike smaller stars which burn fuel steadily over billions of years, red supergiants consume their nuclear fuel at a far faster pace, causing them to expand to astonishing sizes. The enormous radius of VV Cephei A is the result of this accelerated fusion of heavier elements in its core, a process that begins once hydrogen, the simplest and most abundant element in stars, is depleted. As a star ages, its outer layers swell, causing the surface temperature to drop relative to younger, hotter stars like our sun. This cooling produces the signature red hue that makes it visually distinct when observed through instruments capable of detecting color and light intensity across vast distances. Its sheer scale is astonishing, not just in terms of radius, but in terms of mass and volume. Though exact measurements vary due to the complexities of observing stars so far away, estimates suggest that VV Cephei A's radius could range from 1,000 to 1,900 times that of the Sun, and its mass is likely tens of times greater than our Sun. To visualize this, consider that if VV Cephei A were placed at the center of our solar system, its outer surface would engulf not only Mercury, Venus, Earth, and Mars, but also Jupiter, and in some estimates even reach as far as Saturn. The enormity of this star is staggering, and even small variations in measurement can drastically alter our perception of its scale. It is this kind of star that forces us to reconsider what we think we know about size and distance, pushing the limits of our imagination and the tools of modern astronomy alike. VV Cephei A is not merely an isolated giant. It exists in the broader context of the galaxy and is part of a binary star system, a fact that adds to its intrigue. Its placement in the constellation of Cepheus makes it relatively easy for astronomers to locate in the northern sky, though observing its true scale requires sophisticated instruments and careful analysis. The 5,000 light-year distance means that the photons reaching our telescopes today departed the star millennia ago, long before humans built telescopes or even conceived of the possibility of stars of such magnitude. Yet, thanks to advancements in technology and methodology, we can infer its properties with increasing precision, even if some uncertainties remain. Observations of its light, spectrum, and interactions with its companion star allow astronomers to calculate its temperature, radius, luminosity, and mass, revealing a star that is as enigmatic as it is magnificent. The physical characteristics of VV Cephei A
also shed light on its evolutionary trajectory. As a red supergiant, it has expanded from a smaller, hotter main sequence star into the vast, low-density giant we observe today. Its core is now engaged in the fusion of heavier elements, such as helium, carbon, and oxygen, producing the energy necessary to sustain its enormous outer envelope. However, this stage is inherently unstable. The outward pressure from nuclear fusion is balanced precariously against the inward pull of gravity, and slight changes in core conditions can cause pulsations in the star's outer layers. These pulsations manifest as variations in brightness, detectable by astronomers as they carefully monitor its light over extended periods. Such observations not only confirm its status as a red supergiant, but also provide critical insight into the complex physical processes governing the lives of massive stars. The star's location in Cepheus is more than just a celestial address. It situates VV Cephei A within a region of the galaxy that is rich in other stellar phenomena, including clusters, nebulae, and other massive stars. Its relative isolation within this region allows astronomers to study it without excessive interference from nearby bright stars, though its faint visual magnitude requires precision instruments to detect. By combining data from multiple observatories and using techniques such as interferometry, which synthesizes the resolving power of multiple telescopes, astronomers can measure its angular diameter and estimate its physical size, despite the enormous distance. These techniques are particularly important for objects like VV Cephei A, where even minor inaccuracies in measurement can lead to significant differences in our understanding of its dimensions and properties. Beyond its physical attributes, VV Cephei A captivates the imagination because it serves as a window into the extremes of stellar life. Studying such a massive red supergiant helps scientists understand how stars evolve under conditions of extreme mass and size, how they shed material through stellar winds, and how they ultimately end their lives in spectacular supernova explosions. Its existence demonstrates the diversity of stars in our galaxy, showing that while our Sun is a relatively ordinary G-type star, the universe also produces giants of almost unimaginable proportions. Observing VV Cephei A and unraveling its mysteries provides context for understanding not just red supergiants themselves, but also the forces that shape galaxies, distribute elements throughout space, and drive the life cycles of stars on a cosmic scale. In many ways, VV Cephei A embodies the awe-inspiring power of astrophysics, a star that seems almost fictional in its magnitude, yet is entirely real. Its enormous size, remote location, and dynamic physical processes make it an ideal subject for both scientific inquiry and public fascination. By focusing on this red supergiant, we gain not only an appreciation for the grandeur of the cosmos, but also a deeper understanding of the mechanisms that govern the life and death of stars far beyond our solar system. VV Cephei A reminds us that even in the vastness of the galaxy, certain stars can dominate both space and imagination, challenging astronomers to develop new tools and theories capable of explaining objects that stretch the limits of what we thought possible. Its story, while grounded in science, is also a narrative of scale, endurance, and cosmic inevitability. Every photon of light traveling from VV Cephei A to Earth carries with it a tale of immense temperatures, pressures, and gravitational forces. Each observation, each measurement, and each theoretical model contributes to a growing picture of a star that, while distant, profoundly shapes our understanding of stellar physics. And as we continue to study VV Cephei A, we are reminded that the universe is vast, diverse, and often stranger than our imaginations can encompass, where even a single star can dwarf entire solar systems in size and complexity. VV Cephei A, despite its titanic size, does not exist in isolation. It is part of a fascinating and complex binary system, paired with a smaller yet remarkably significant companion known as VV Cephei B. This pairing transforms the system from being a simple example of a solitary red supergiant into a cosmic laboratory, offering astronomers a unique opportunity to study interactions between stars of vastly different masses, temperatures, and evolutionary stages. The contrast between the enormous, cool, red VV Cephei A and the much smaller, hot blue VV Cephei B creates a dynamic system where gravitational forces, radiation, and stellar winds interact in ways that are both beautiful and scientifically revealing. While VV Cephei A dominates the visual and physical scale of the system, the presence of VV Cephei B is crucial in helping astronomers measure and understand the true characteristics of its giant companion. VV Cephei B is classified as a blue main sequence star, which means it is relatively young, hot, and luminous compared to VV Cephei A. Its surface temperature is far higher than that of the red supergiant, glowing with intense blue-white light that stands in stark contrast to the deep crimson of VV Cephei A. While VV Cephei A has expanded to colossal dimensions, VV Cephei B remains compact, with a radius only a fraction of its partners, though still considerably larger than the Sun. Estimates suggest it has about 13 times the mass of our Sun, a remarkable figure in its own right, but small when compared to the mass and volume of VV Cephei A. This disparity creates a striking example of how different stars evolve depending on their initial mass and internal physics. Observing such a system allows astronomers to study phenomena like mass transfer, orbital dynamics, and eclipses in a setting that is extreme but measurable. The stars orbit each other in a long-period elliptical orbit, completing one full cycle approximately every 20.3 years. The immense separation between them, combined with the extreme size of VV Cephei A, produces gravitational and radiative interactions that can be studied over decades. Although VV Cephei B is far smaller than its red supergiant companion, it is not insignificant. Its gravitational pull contributes to the shaping of the red supergiant's outer layers and the dynamics of the material lost through stellar winds. This orbital relationship also plays a crucial role in revealing the properties of VV Cephei A itself. By studying the motion of VV Cephei B, astronomers can infer mass, density, and even aspects of VV Cephei A's internal structure, information that would be impossible to obtain from a solitary supergiant. One of the most fascinating aspects of this binary system is the phenomenon of eclipses. At regular intervals, VV Cephei E passes behind or in front of VV Cephei A from our line of sight, causing measurable dips in the system's overall brightness. These eclipses are more than a visual curiosity. They provide essential data that help scientists calculate the star sizes, orbital inclination, and relative distances. Because VV Cephei A is so enormous and VV Cephei B is so luminous in its own right, the timing and depths of these eclipses become a natural experiment in astrophysics. By monitoring changes in the light curve, astronomers can detect subtle interactions, including variations in the red supergiant's outer atmosphere, the flow of gas from one star to another, and even pulsations caused by the immense internal pressures within VV Cephei A.
The binary nature of the system also has profound implications for the future evolution of both stars. While VV Cephei A is in the final stages of its life, the presence of a companion could influence how it loses mass and eventually explodes as a supernova. If VV Cephei A were truly isolated, it might shed material symmetrically into space, but the gravitational influence of VV Cephei B can distort the star's envelope, channeling stellar winds and ejected matter in preferential directions. This means that when the inevitable supernova occurs, the resulting explosion and material distribution will not only reflect the properties of VV Cephei A itself, but also the intricate gravitational ballet with its companion. Studying binary systems like this provides a rare window into the interactions that shape some of the most extreme stellar events in the universe. Beyond its scientific value, the relationship between VV Cephei A and VV Cephei B also underscores a broader lesson about the cosmos. Size and mass are not the only determinants of significance. VV Cephei B, though dwarfed by its red supergiant companion, plays a crucial role in revealing VV Cephei A's mysteries. Its light, motion, and interaction with the giant allow astronomers to probe the dynamics of one of the largest known stars in the universe, offering a unique opportunity to understand phenomena that would otherwise remain hidden. In a way, the two stars complement each other, forming a system where the small helps us comprehend the immense, and the fast-moving and luminous illuminates the slow, vast, and fading. This binary system also highlights the rarity of such arrangements. While massive stars are not uncommon in the galaxy, systems in which a supergiant is paired with a smaller, hot companion in a configuration suitable for precise observation are exceptionally rare. The combination of orbital dynamics, eclipses, and contrasting stellar types creates a natural laboratory for studying stellar evolution under conditions that cannot be replicated on Earth. Through decades of monitoring, astronomers continue to refine models of the system, testing theories about mass loss, radiative pressure, and the ultimate fate of massive stars. The findings from VV Cephei A and B inform our understanding of not just this particular system, but of binary star dynamics and red supergiant evolution throughout the universe. The existence of a companion star also adds layers of complexity to interpreting VV Cephei A's light. Its immense size, combined with the variable contribution of VV Cephei B's blue light, means that observations must account for overlapping signals. Detailed photometric and spectroscopic studies have revealed not just eclipses, but also subtle changes in the red supergiant's outer atmosphere caused by tidal interactions and the gravitational pull of its smaller companion. This makes VV Cephei not only one of the largest stars in the universe, but also one of the most dynamic and complex to study, with a system that challenges our observational techniques and theoretical models alike. In essence, VV Cephei A cannot be fully understood without acknowledging the presence of VV Cephei B. The binary system exemplifies the intricate interplay of stars in close quarters, where gravity, radiation, and mass loss combine to create a system far richer than the sum of its parts. The companion star, though small compared to the supergiant, acts as a mirror, revealing hidden aspects of VV Cephei A's structure, behavior, and ultimate fate. It is this partnership, this cosmic dance, that makes the VV Cephei system such a compelling subject of study and imagination, a place where the enormous and the comparatively modest coexist to teach us about the universe's grandeur. The enormity of VV Cephei A becomes even more striking when compared directly with our familiar Sun. While the Sun, a G-type main sequence star, serves as the life-giving center of our solar system, VV Cephei A dwarfs it in ways that stretch the imagination. Estimates place the red supergiant's radius at anywhere from 1,000 to 1,900 times that of the Sun, meaning that a single stretch from its core to its outer atmosphere could span a distance that would encompass nearly the entire planetary system as we know it. To put this in perspective, consider that the radius of the Sun is roughly 696,000 kilometers. Multiplying that by even the conservative lower estimate of 1,000 gives a staggering 696 million kilometers, roughly the distance from the Sun to just beyond Jupiter's orbit. If we consider the upper estimate of 1,900 times the Sun's radius, we are looking at a diameter approaching 2.6 billion kilometers, potentially reaching the orbit of Saturn, which is nearly 1.43 billion kilometers from the Sun. The sheer scale is almost unfathomable, turning our mental models of planetary distances into something almost childishly small in comparison. Visualizing this enormous size is challenging, but a few mental exercises help illustrate it. If we replace the Sun with VV Cephei A in the center of our solar system, Mercury, Venus, Earth, and Mars would be entirely engulfed by the star's outer layers. Jupiter, the solar system's largest planet, would be deep inside the star's atmosphere, experiencing conditions of unimaginable pressure and heat
far beyond what we can reproduce or endure on Earth. Saturn, depending on which size estimate you use for VV Cephei A, could also find itself swallowed within the star's fiery red envelope. Our entire planetary neighborhood, with all its familiar orbits and distances, would fit comfortably inside the sprawling reaches of this single star. Even the notion of a solar system as we know it seems almost laughably tiny when measured against the backdrop of a star of this magnitude.
Another way to grasp the scale is to compare the volumes of the two stars. The volume of a sphere increases with the cube of its radius, so even a seemingly modest increase in size results in an enormous jump in volume. At the lower end of its estimated radius, 1,000 times the Sun, VV Cephei A's volume would be about 1 billion times greater than the Sun's. At the upper end of 1,900 solar radii, its volume would surpass the Sun's by nearly 7 billion times. This staggering difference means that VV Cephei A could physically contain billions of suns within its vast interior. Attempting to imagine that is a dizzying exercise, one that forces us to confront the limits of human intuition. It's a scale so vast that the concepts of distance and size we're comfortable with on Earth or within our solar system almost completely break down. To translate this scale into temporal terms, consider how long it would take to travel around the surface of such a star. A commercial jet flying at roughly 900 kilometers per hour would require over 20 years to circumnavigate VV Cephei A at its equator, assuming it could fly safely through the thin but extremely hot stellar atmosphere. Even light, which travels at 299,792 kilometers per second, would take nearly 7 hours to cross the star from one edge to the other if we adopt the larger radius estimate. This is a scale so immense that it defies not only direct visualization, but also common experience with speed, distance, and size, placing VV Cephei A in an almost mythic category of cosmic giants. Despite its colossal dimensions, VV Cephei A is relatively faint to the naked eye from Earth, a reminder of just how far away it is, about 5,000 light-years. The fact that such a massive object appears as a mere point of light in our sky underscores the vastness of the universe and the incredible distances that separate us from even the largest and most powerful stars. Its size is not just a curiosity. It plays a critical role in understanding the physical processes occurring within the star, such as energy generation, convection, mass loss, and the dynamics of its expanding outer layers. A star of this magnitude experiences extreme gravitational and radiative forces, leading to pulsations, instabilities, and the intense stellar winds that gradually strip away its outer layers. Comparisons with other known stars further highlight VV Cephei A's exceptional scale. While the Sun is a relatively ordinary star, even among main sequence stars, VV Cephei A belongs to the rarefied class of red supergiants, objects that represent some of the largest, most luminous, and most short-lived stars in the universe. It is far larger than well-known red supergiants such as Betelgeuse and Orion, or Antares and Scorpius, whose diameters are a few hundred times that of the Sun. VV Cephei A, with its extreme dimensions, is truly in the upper echelon of stellar sizes, rivaled only by a handful of other supergiants like UY Scuti and YV Canis Majoris. These comparisons help astronomers place VV Cephei A in context and highlight how unique such stars are, both in their physical properties and in their role in the galactic ecosystem. It is also worth noting that the immense size of VV Cephei A directly influences its luminosity and surface characteristics. Its enormous radius, combined with a relatively cooler surface temperature of around 3,500 K, produces a massive radiating area, allowing it to emit tremendous energy, primarily in the red and infrared portions of the spectrum. This contrasts sharply with smaller, hotter stars like the Sun, which radiate more in the yellow and visible spectrum. The interplay of size and temperature makes VV Cephei A a deep red, luminous, and visually striking object in infrared surveys, even if it remains faint to unaided human eyes. The star's dimensions dictate the behavior of its outer layers, the extent of its convective zones, and the intense stellar winds that carry away material into the surrounding interstellar medium. Understanding the scale of VV Cephei A is not just an exercise in numbers. It is essential for grasping the physical phenomena at work.
Its enormous size means that gravity at its surface is relatively weak compared to smaller stars, allowing for massive amounts of material to escape into space. Its enormous volume and surface area mean that the mechanisms of energy transport, convection, and mass loss operate on scales vastly different than those in the Sun. By comparing the Sun, a stable middle-aged star, with a red supergiant like VV Cephei A, astronomers gain crucial insight into how stars evolve, expand, and ultimately approach the violent end of their lives.
In essence, the sheer size of VV Cephei A is a gateway to understanding not only the extremes of stellar evolution, but also the breathtaking scale of the cosmos itself. By placing this single star in the context of our solar system, we begin to comprehend a universe where one star alone can outsize everything familiar to us on an almost unimaginable scale, dwarfing planets, eclipsing light travel distances, and challenging our very sense of perspective. It is a star that not only dominates its own neighborhood, but also commands our awe, curiosity, and respect, serving as a powerful reminder of the immense variety and magnitude of objects in the universe. To truly grasp the scale of VV Cephei A, words alone must stretch to their limits, for numbers and distances at this level can feel abstract and almost meaningless without context. While we can recite that its radius is over 1,000 times that of the Sun, such figures remain difficult to internalize. It helps to translate these cosmic measurements into analogies and mental images that bring the incomprehensible into a form our minds can at least attempt to comprehend. For instance, imagine taking the Sun, the star that dominates our sky and governs life on Earth, and shrinking it down to the size of a small bead. Tiny, almost insignificant in your hand. Now consider VV Cephei A in the same scale. It would be a sphere so massive, so enormous, that it could easily dwarf a football stadium, stretching far beyond the reach of the stands and the field, encompassing an area where tens of thousands of spectators would seem utterly minuscule. This analogy begins to give a sense of the physical space the star occupies, and yet even this mental image only scratches the surface of its true enormity. Light, the fastest phenomenon in the universe, behaves in ways that remind us of the scale we are dealing with. Even at its near incomprehensible speed of nearly 300,000 kilometers per second, it would take hours to traverse the distance from one edge of VV Cephei A to the other. In practical terms, this means that if a photon were born on one side of the star's outer layer, it could journey for more than 7 hours before reaching the opposite side. To place this in human terms, 7 hours is enough time to fly across continents, watch an entire workday pass, or complete a long-haul flight. But on the scale of VV Cephei A, that same time only allows light to move from one edge of the star to the other. The vast distances inside a single star of this magnitude challenge our perception of space and time, emphasizing just how alien and extreme the environments of supergiants are compared to anything in our solar system. If we imagine attempting to traverse VV Cephei A, the scale becomes almost absurd. A commercial jet traveling at roughly 900 kilometers per hour, moving continuously and without pause, would require more than 20 years to circumnavigate the star at its equator. 20 years to circle a single star is a concept so far removed from everyday human experience that it strains the mind to imagine. The journey would cover billions of kilometers over decades, passing through layers of incandescent gas far hotter and more turbulent than any terrestrial environment. The idea that a single star could present such a gargantuan surface area, where a journey that spans continents on Earth becomes insignificant, underscores the truly cosmic scale we are discussing. VV Cephei A is so vast that conventional comparisons fail. Planets, moons, and even entire solar systems are mere specks in comparison. For example, the distance from the Earth to the Sun, approximately 150 million kilometers, would barely span the outer layers of VV Cephei A. Jupiter, our solar system's largest planet, would be engulfed within its atmosphere, and Saturn might just graze the outer fringes. Trying to picture these celestial relationships in everyday terms, like beads, stadiums, and commercial jets, allows our minds to bridge the gulf between human scale and cosmic scale, even if only partially. It is in these kinds of mental exercises that the immensity of the star begins to become tangible. Even time behaves differently at this scale. Pulsations, convection currents, and massive ejections of stellar material occur over periods that feel almost geological compared to human lifespans. Surface disturbances, storms, and gas flows on VV Cephei A span hundreds or thousands of kilometers, dwarfing any storm system on Earth or even Jupiter's Great Red Spot. The star's atmosphere is a boiling, turbulent environment stretching across incomprehensible distances, yet the light escaping from it eventually reaches us as a single, faint speck in the night sky. Understanding this perspective is critical. VV Cephei A is both enormous and distant, massive yet delicate in its outer layers, turbulent yet graceful in its motion through space. These analogies and mental exercises are not just thought experiments. They are essential for bringing the human mind close to comprehending the scale of the universe. Numbers like 1,000 to 1,900 solar radii are abstract and difficult to grasp, but when translated into hours of light travel, decades of jet travel, or spheres larger than football stadiums, the enormity begins to feel almost real. It is a scale that challenges both imagination and language, a reminder that our everyday experiences with size and distance are insignificant when compared to cosmic phenomena. VV Cephei A's colossal size also influences its behavior and structure. Its outer layers are tenuous compared to its dense core, and the enormous radius allows for convective cells so vast that they would dwarf entire continents on Earth. The star's gravity at the surface is relatively weak because of its size, permitting massive amounts of gas to escape in stellar winds that extend millions of kilometers into space. These processes are not mere curiosities, they determine how the star will evolve, how it interacts with its companion in the binary system, and how it will ultimately die in a spectacular supernova. The sheer physical scale of the star magnifies these processes in ways that smaller stars like our Sun cannot replicate, making VV Cephei A a natural laboratory for understanding extreme stellar physics. Even considering the human perspective, the star evokes awe and humility. Standing metaphorically at its surface, if such a thing were possible, the sky would be incomprehensibly vast, filled with glowing layers stretching beyond the horizon. Light from its core would take hours to reach the surface, and the turbulence of its atmosphere would dwarf anything familiar. In many ways, thinking about VV Cephei A forces a reevaluation of our place in the universe. The human-scale experiences of travel, time, and distance become nearly meaningless when faced with a star whose very existence stretches across distances and durations far beyond what we can directly perceive. In essence, VV Cephei A is a demonstration of the universe's power to inspire awe and challenge comprehension. Through analogies, beads and stadiums, light and jet travel, we can begin to feel its vastness, though never fully grasp it. The star is a cosmic monument to scale, a reminder that in the universe, even the largest objects we can see are only a glimpse of the extremes that exist. Its sheer magnitude sets the stage for the other extraordinary aspects of its existence, from its temperature and luminosity to its role in a binary system, its eventual demise in a supernova, and the lessons it imparts on the life cycles of the universe's most massive stars. Understanding the colossal scale of VV Cephei A is not simply a matter of imagination or analogy. It is grounded in precise scientific measurement and observational techniques that astronomers have refined over decades. Measuring a star that lies 5,000 light-years away and spans a radius thousands of times larger than the Sun presents unique challenges. Unlike planets or nearby celestial objects, we cannot send probes to touch a star or directly measure its surface. Instead, astronomers rely on a combination of indirect methods, primarily the relationships between a star's brightness, temperature, and distance, to infer its true size. The first step is often to determine its apparent brightness, or how much light reaches Earth. This brightness, combined with knowledge of the star's distance, allows astronomers to calculate its intrinsic luminosity, a measure of how much energy the star emits in all directions. For distant stars like VV Cephei A, this is crucial because a star that appears faint may actually be exceptionally luminous if it is far enough away. To calculate a star's size from luminosity, astronomers apply a principle rooted in the Stefan-Boltzmann law, which connects a star's energy output to its surface area and temperature. The law states that the total energy radiated per unit time by a black body is proportional to the fourth power of its temperature and its surface area. By measuring the star's surface temperature, determined through spectral analysis of the light it emits, scientists can solve for the radius. VV Cephei A's deep red color corresponds to a relatively cool surface temperature of around 3500 K, much cooler than the Sun's 5800 K. Despite this cooler temperature, its enormous size compensates, producing an enormous total luminosity. By combining luminosity and temperature, astronomers can derive an estimate of the star's radius with surprising accuracy, even at immense distances. Distance measurement is another critical component. Knowing how far away VV Cephei A is allows astronomers to convert the observed brightness into actual energy output. Parallax, the apparent shift in a star's position against distant background stars as Earth orbits the Sun, is a traditional method for nearby stars. However, at distances of thousands of light years, parallax becomes exceedingly small and difficult to measure directly. For stars like VV Cephei A, astronomers often rely on other distance indicators, such as the star's membership in a known cluster or comparisons with similar stars whose distances are better constrained. These methods carry some uncertainties, which contribute to the variations in size estimates, but advances in technology, including space telescopes and precise astrometric satellites, have significantly improved accuracy in recent decades. A more modern and increasingly powerful tool for measuring giant stars like VV Cephei A is interferometry, which allows astronomers to achieve far higher resolution than a single telescope could provide. Interferometry works by combining light from multiple telescopes separated by significant distances to simulate a much larger instrument, effectively creating a virtual telescope capable of resolving fine details. This technique enables direct measurements of a star's angular diameter, the apparent size of the star in the sky, which, when combined with distance data, can be converted into a physical radius. Interferometry has been instrumental in confirming the vast size of VV Cephei A, providing visual evidence that complements the theoretical calculations based on luminosity and temperature. In addition to radius, interferometric observations can reveal features of the star's atmosphere, such as convective cells, asymmetries, and the presence of extended envelopes of gas, giving further insight into its structure and behavior. Spectroscopy also plays a central role in these measurements. By analyzing the star's light spectrum, astronomers can determine its surface temperature, chemical composition, and radial velocity. The absorption lines in the spectrum indicate the elements present and provide temperature estimates, while shifts in these lines due to the Doppler effect reveal motion toward or away from Earth. When combined with brightness and distance, spectroscopy helps refine the star's radius estimates and can even indicate atmospheric phenomena such as mass loss through stellar winds. For VV Cephei A, this is particularly important because its immense size and the tenuous nature of its outer layers mean that it is constantly shedding material into space. Understanding these processes helps astronomers account for variations in brightness and improves the accuracy of radius calculations. Astronomers also observe light curves, tracking changes in the star's brightness over time. While light curves are especially useful for detecting binary companions or variable stars, they also provide indirect clues about size and structure.
In the case of VV Cephei A, fluctuations in brightness can result from pulsations in the outer layers or eclipses caused by its companion, VV Cephei B. By modeling these variations, scientists can refine measurements of the star's radius and even learn about the geometry of its outer envelope. Combining light curve analysis with interferometry, spectroscopy, and brightness distance calculations creates a multifaceted, cross-verified approach that gives astronomers confidence in their estimates even for stars hundreds of thousands of times more distant than planets within our own solar system. Despite these advanced methods, measuring a star as extreme as VV Cephei A remains challenging. Different techniques can yield slightly different results, which is why estimates of its radius range from 1,000 to 1,900 times the Sun's radius. Variations arise from uncertainties in distance, the star's non-uniform surface, and dynamic changes in the outer layers caused by pulsation or mass loss. Nevertheless, by using multiple complementary methods, astronomers have built a coherent picture of VV Cephei A as one of the most massive and extensive stars known. Its measurement is not merely a triumph of technology. It is a testament to human ingenuity, the ability to infer properties of objects so distant and extreme that direct measurement would otherwise be impossible. Ultimately, these techniques do more than quantify size. They reveal the star's physical reality and behavior. VV Cephei A's massive radius explains its low surface gravity, its enormous convective cells, and the strong stellar winds that gradually shed material into the surrounding space. Interferometric observations can even hint at the asymmetries in its atmosphere, suggesting complex interactions with its companion and internal dynamics that influence how the star will eventually evolve and die. By combining brightness, temperature, distance, and high-resolution imaging, astronomers turn abstract numbers into a tangible understanding of a star so large it can contain entire planetary systems within its expanse. The process of measuring VV Cephei A exemplifies the interplay between observation, theory, and technology in modern astronomy. It demonstrates how, through careful application of physics and creative observational methods, we can gain insight into objects whose scales dwarf the imagination. From spectroscopy and light curves to interferometry and distance modeling, each tool adds a layer of understanding, allowing us to peer into the heart of a star whose size, behavior, and life cycle challenge both our intuition and the limits of current scientific knowledge. VV Cephei A stands not only as a monument to the universe's scale, but also as a testament to humanity's ability to explore, quantify, and comprehend phenomena far beyond the confines of our everyday experience.
VV Cephei A occupies a fascinating and prestigious position among the largest stars known to humanity. Yet it is part of a small, exclusive club of cosmic giants whose dimensions challenge not only the imagination, but also the limits of modern observational astronomy. Stars like UY Scuti, VY Canis Majoris, and Betelgeuse are often mentioned in the same breath as VV Cephei A, but each has its own unique properties, histories, and degrees of uncertainty in measurement, making direct comparisons both intriguing and complex. Among this class of red supergiants, small changes in assumptions about distance, temperature, or luminosity can drastically alter a star's perceived size, meaning that the largest star in the universe is a moving target in the scientific community. In that context, VV Cephei A is not only remarkable for its massive radius, but also for its consistency as a member of the extreme upper echelon of stellar giants, earning its place among the most awe-inspiring objects in the cosmos. UY Scuti, for example, has often been cited as one of the largest known stars, with estimates placing its radius at approximately 1,700 times that of the Sun. This staggering size puts it in a similar league as VV Cephei A, though direct comparison is complicated by differences in observational methods, the star's pulsation cycles, and uncertainties in distance. UY Scuti is relatively bright in the infrared spectrum and exhibits significant variability, which can cause fluctuations in its measured size over time. As a result, while some studies suggest it is slightly larger than VV Cephei A, others place VV Cephei A at the top, illustrating how the rankings among these supergiants are provisional and subject to refinement as observational techniques improve. The subtle differences in measurement highlight the challenge astronomers face. We are attempting to quantify objects whose surfaces are diffuse, dynamic, and often not spherical, making traditional notions of radius and volume imperfect descriptors. VY Canis Majoris is another famous contender, a hypergiant whose size estimates have historically placed it among the most massive stars known. VY Canis Majoris boasts an incredibly luminous output, but measuring its radius is complicated by a dense, extended envelope of gas and dust surrounding the star. While initial estimates suggested it could reach 2,000 solar radii, later studies, accounting for its complex atmosphere, have often revised that figure downward, demonstrating how dependent these measurements are on modeling assumptions. In this context, VV Cephei A, though perhaps slightly smaller than some early estimates for VY Canis Majoris, has the advantage of being part of a well-studied binary system, allowing astronomers to cross-reference orbital dynamics and eclipses to refine its radius with a degree of confidence that is difficult to achieve for more isolated hypergiants. Then there is Betelgeuse, a red supergiant in the constellation Orion that has captured both public imagination and scientific attention. With a radius roughly 900 times that of the Sun, Betelgeuse is smaller than VV Cephei A, but still immense by any conventional standard. It is closer to Earth, about 642 light-years away, which makes detailed observations of its surface and atmosphere easier. Betelgeuse has been crucial in studying red supergiant behavior, including surface convection, stellar pulsations, and mass loss, providing a model for understanding more distant and extreme stars like VV Cephei A. While VV Cephei A is much larger and more massive, Betelgeuse's relative proximity allows astronomers to test and calibrate techniques that can then be applied to giants farther away, bridging the gap between observation and theoretical modeling. One of the most intriguing aspects of comparing VV Cephei A to these other giants is how dynamic the rankings can be. Stars are not static objects. They pulsate, lose mass through stellar winds, and may even expand or contract over time. Consequently, a star that seems to be the largest at one moment may not hold that title decades later. Variations in measurement techniques further complicate the picture. For example, interferometry, spectrophotometry, and modeling of eclipsing binary dynamics can all yield slightly different results. This means that lists of the largest stars in the universe are provisional, continually revised as astronomers develop more precise methods and obtain better data. VV Cephei A sits at the intersection of this uncertainty. Its vastness undeniable, but exact size still subject to refinement, highlighting both the challenges and the excitement of studying such extreme objects.
The comparison of these giants is not merely academic. It reveals fundamental truths about stellar evolution. Red supergiants like VV Cephei A, UY Scuti, and VY Canis Majoris, and Betelgeuse share a common trait. They are in advanced stages of stellar life, having exhausted hydrogen in their cores and expanded dramatically. Their enormous radii and low surface gravity are consequences of these evolutionary processes, and their comparison helps scientists understand the physics governing energy transport, mass loss, and eventual supernova events. By studying multiple red supergiants, astronomers can identify patterns and anomalies, learning not just about individual stars, but about the broader population of massive stars in our galaxy and beyond. VV Cephei A stands out among these giants because of its binary nature and the high-quality data that comes from observing eclipses and orbital dynamics. While UY Scuti and VY Canis Majoris are often studied in isolation, VV Cephei A's companion, VV Cephei B, provides a reference point that makes its radius, mass, and atmospheric behavior easier to quantify. This is a critical advantage because even small errors in distance or temperature can dramatically affect radius estimates for stars of this size.
The fact that VV Cephei A can be observed and measured within a binary system adds a layer of precision that is rare among stars of its magnitude, strengthening its standing in the cosmic hierarchy of giants. Finally, comparing VV Cephei A to other record holders helps illustrate the staggering diversity of stars in our universe. While all of these stars belong to the red supergiant category, each has unique features, differences in mass, luminosity, atmospheric composition, variability, and binary interactions. These differences remind us that even among the largest and most extreme stars, the cosmos favors variety, producing objects that are both awe-inspiring and scientifically invaluable. VV Cephei A, UY Scuti, VY Canis Majoris, and Betelgeuse together represent the upper limits of stellar scale and the complex interplay between observation, modeling, and cosmic reality. In essence, VV Cephei A's place among other giants underscores both its immensity and its importance. It is a member of a select group of stars that push the boundaries of our understanding of size, energy, and stellar life cycles. Yet its measurements remain dynamic, its ranking fluid, and its mysteries compelling. It is not just about being the largest, but about understanding how such stars live, interact, and eventually die, contributing to the ongoing story of the universe. VV Cephei A's comparison to its peers amplifies the awe it inspires and the scientific value it holds, demonstrating that even among giants, each star is a world unto itself, with lessons to teach and enigmas to unravel. VV Cephei A's most immediately striking feature, beyond its incomprehensible size, is its deep red color, which signals both its temperature and its stage in stellar evolution. Unlike our Sun, which burns a steady yellow-white at a surface temperature of roughly 5,800 K, VV Cephei A emits a cooler crimson glow with a surface temperature of about 3,500 K. This relatively low temperature for such a large star is what gives it the red supergiant classification. The redness is not merely aesthetic. It tells astronomers a great deal about the physical processes occurring within and on the surface of the star. Cooler temperatures result from the star's vast expansion. As a star grows larger, the energy generated in the core spreads over an ever-increasing surface area, lowering the overall temperature felt at the outer layers. In this way, the red hue of VV Cephei A is a visible indicator of its enormous scale and advanced evolutionary stage.
The red color of VV Cephei A also serves as a clue about the star's internal processes. Red supergiants are in a late phase of stellar life, having exhausted the hydrogen fuel in their cores. Without hydrogen fusion to provide the outward pressure that counteracts gravity, the core contracts and heats up, while the outer layers expand massively, lowering the surface temperature. The star begins fusing heavier elements, such as helium, carbon, and oxygen, creating the energy that powers the extended outer envelope. This expansion and cooling of the outer layers is what shifts the emitted light toward longer wavelengths, producing the deep red or crimson glow we associate with red supergiants. To the human eye, this color is subtle and faint when observed across the thousands of light years separating us from VV Cephei A, but infrared instruments reveal its true intensity and richness. Despite the cooler surface temperature, VV Cephei A is incredibly luminous, thanks to its enormous size. The star's luminosity depends not just on temperature, but also on surface area. The larger the star, the more total energy it radiates. In this way, a cooler star can outshine a hotter star if its radius is sufficiently vast. VV Cephei A, with its radius over 1,000 times that of the Sun, emits enormous amounts of energy across visible and infrared light, making it detectable even at extreme distances. Its reddish light is also strongly influenced by the star's extended atmosphere, which contains layers of cooler gas and dust that absorb and re-radiate energy, subtly modifying the spectrum astronomers observe. The cool surface temperature has other implications as well. It contributes to the stability and dynamics of the star's outer layers, allowing convective currents to form on scales unimaginable compared to smaller stars. These convection cells, each potentially spanning hundreds of millions of kilometers, transport energy from the interior to the surface and drive turbulence in the star's extended atmosphere. The result is a constantly shifting and dynamic surface, where pockets of hotter and cooler gas create subtle variations in brightness and even slight asymmetries in shape. This variability, when observed over time, helps astronomers understand not just the surface conditions, but also the internal physics of red supergiants like VV Cephei A. The color also provides insight into the chemical processes occurring in the star. At these cooler temperatures, molecules can form in the outer layers that would not survive in hotter stars. Compounds like titanium oxide absorb specific wavelengths of light, enhancing the reddish appearance of the star. Spectroscopic studies of VV Cephei A reveal these chemical signatures, confirming its classification as a red supergiant and providing information about the composition of its outer envelope. This chemical information is critical, as it informs astronomers about how the star is shedding material and enriching the surrounding interstellar medium with elements essential for the next generation of stars and planets. VV Cephei A's red hue is also a visual reminder of its evolutionary trajectory. Unlike hotter, blue stars that burn fast and die young, red supergiants are approaching the final stages of their lives. The cooler surface signals a star that has expanded to an enormous size, exhausted the simpler fuels in its core, and begun fusing heavier elements in a complex chain of nuclear reactions. This is a fleeting stage in cosmic terms. Red supergiants are relatively short-lived, existing in this swollen, cool state for only a few 100,000 to a million years. A brief moment compared to the billions of years a star like the Sun spends on the main sequence. In this sense, the deep red color of VV Cephei A is a kind of cosmic timestamp, marking it as a star in its twilight years, poised for eventual collapse and supernova. Observing this color from Earth requires careful instrumentation. At a distance of roughly 5,000 light-years, VV Cephei A appears faint to the naked eye, but its spectrum in visible and infrared wavelengths clearly indicates a deep red star. The intensity and hue of this red light, when analyzed with spectroscopic tools, allow astronomers to determine surface temperature and other properties with precision. Comparing its spectral signature to those of other red supergiants also helps refine models of stellar structure, mass loss, and future evolution, providing a window into processes that cannot be directly observed in more distant or smaller stars. In short, the deep red hue and cool temperature of VV Cephei A are inseparable from its identity as a red supergiant. They reveal the star's scale, internal physics, and evolutionary stage while providing a rich dataset for astronomers studying the extremes of stellar life. The color is a sign of both beauty and impending transformation. It marks a star that is enormous, luminous, and majestic, yet also unstable and approaching the dramatic climax of its life cycle. The crimson glow is a silent testimony to the forces shaping the star from within and to the cosmic processes that govern the life and death of the universe's most massive objects. VV Cephei B, the companion star to the enormous red supergiant VV Cephei A, provides a fascinating contrast in both size and temperature, highlighting the diversity and complexity of binary star systems. While VV Cephei A dominates the system in terms of sheer volume, VV Cephei B is a hot blue main sequence star, significantly smaller but remarkably important for understanding the dynamics of the system. Its blue-white light indicates a surface temperature far higher than the cooler 3500 K of VV Cephei A, likely exceeding 20,000 K, placing it among the hotter and more massive main sequence stars. This temperature difference creates a striking visual contrast and a dynamic interplay of light and radiation within the binary system, making the VV Cephei pair a unique laboratory for studying stellar interactions. Mass is one of the most critical characteristics of VV Cephei B. With an estimated 13 times the mass of the Sun, it is a heavyweight in its own right, although its radius is tiny compared to the sprawling red supergiant. Despite being physically smaller, VV Cephei B's mass gives it a significant gravitational influence over the system, affecting the orbit of VV Cephei A and interacting with the outer layers of the giant star. This gravitational tug, combined with radiation from the hot, energetic star, can induce distortions in VV Cephei A's enormous outer envelope, shaping the stellar winds and even contributing to observable asymmetries in the supergiant's atmosphere.
In essence, VV Cephei B is small but potent, a key player in determining the behavior and structure of the binary system. The two stars are bound in an elliptical orbit with a period of approximately 20.3 years, meaning that once every 2 decades, the companion completes a full orbit around the red supergiant. The orbit is not perfectly circular, which leads to varying distances between the stars throughout their journey. At closest approach, known as periastron, the gravitational interactions between the two stars are strongest, sometimes intensifying the transfer of mass from VV Cephei A's outer layers toward its companion. These periodic changes in distance also affect the observed light of the system, contributing to subtle variations in brightness that astronomers track over long periods to refine models of both star sizes, masses, and atmospheric dynamics. The presence of VV Cephei B has allowed astronomers to study VV Cephei A with greater precision than would be possible if the supergiant were isolated. By observing the motion of the smaller, luminous companion, scientists can calculate the mass and orbital parameters of both stars using principles of celestial mechanics. This in turn enables estimates of VV Cephei A's mass, which is otherwise difficult to measure directly due to its enormous radius and diffuse outer layers. The binary relationship acts as a natural calibration tool, helping to constrain models of the red supergiant's structure, evolution, and eventual fate. VV Cephei B also plays a significant role in the observable phenomena of the system, particularly in eclipses and light curve variations. During its orbit, it periodically passes in front of or behind VV Cephei A from Earth's perspective, causing dips in the system's overall brightness. These eclipses, which are subtle but measurable, provide astronomers with critical data about the relative sizes of the stars, the geometry of their orbit, and the nature of VV Cephei A's extended atmosphere. Observing these eclipses over multiple orbital periods has allowed scientists to refine their understanding of the star's masses, radii, and separation, producing one of the most detailed models of a red supergiant and its companion in the galaxy. The interplay between VV Cephei A and B is not purely gravitational. The intense radiation emitted by the hot blue companion can influence the outer layers of the red supergiant, heating regions of its atmosphere and potentially driving localized stellar winds. This interaction, while subtle, can shape the morphology of VV Cephei A's envelope and create regions of enhanced mass loss. Additionally, the orbit of VV Cephei B ensures that these interactions are dynamic, changing over time as the stars approach and recede from each other. Studying these effects helps astronomers understand how massive stars interact with companions and how binary dynamics can influence stellar evolution, particularly in systems where one star is approaching the end of its life. The relationship between the two stars also has implications for the ultimate fate of the system. When VV Cephei A eventually reaches the supernova stage, the presence of VV Cephei B could drastically influence the distribution of material ejected in the explosion. Its gravitational pull could channel the supernova ejecta, and depending on the proximity during the explosion, it might even lose part of its outer layers or experience a dramatic alteration in orbit. This potential outcome underscores the importance of VV Cephei B. While it may appear secondary in size and visual dominance, it is intimately involved in shaping both the current dynamics and future evolution of the system. In addition to its scientific significance, VV Cephei B emphasizes the diversity of stars in the universe. Within a single system, we witness extremes: a sprawling red supergiant on the brink of collapse, paired with a compact, hot, and energetic main sequence star. This juxtaposition highlights how stars of very different masses and evolutionary stages can coexist and interact, offering astronomers a microcosm of the complexities of stellar populations and binary interactions. The system challenges simplistic notions of stars as solitary, isolated objects, and illustrates the rich dynamics that emerge when multiple massive objects coexist within a shared gravitational domain. The blue companion, with its smaller size, high temperature, and significant mass, is therefore far from a mere supporting character in the story of VV Cephei A. Its presence allows scientists to measure and model the supergiant, observe eclipse phenomena, track mass transfer, and predict how the system might evolve after the inevitable supernova event. It provides context, contrast, and calibration, a necessary anchor that transforms a distant, gargantuan star into a more comprehensible, quantifiable, and scientifically rich object of study. Without VV Cephei B, many of the insights we currently have about VV Cephei A's size, mass, and behavior would remain elusive, leaving the largest red supergiants of the galaxy shrouded in even greater mystery. One of the most fascinating aspects of the VV Cephei system is the eclipse phenomenon, a regular dimming of the system's brightness caused by the orbital motion of VV Cephei B relative to the enormous red supergiant VV Cephei A. Unlike solitary stars, whose brightness remains relatively stable, binary systems often display characteristic fluctuations in light due to one star passing in front of or behind the other from our vantage point on Earth. In the case of VV Cephei, these eclipses were a key clue that astronomers used to identify the system as a binary star, long before the individual stars could be resolved directly. By carefully monitoring the dips in brightness, scientists could deduce the presence of a companion star even at a distance of thousands of light years, making the eclipses a natural cosmic experiment in celestial mechanics.
The eclipses occur because VV Cephei B, the smaller but intensely luminous blue star, periodically passes either in front of or behind VV Cephei A in its 20.3-year orbit. When the companion moves behind the supergiant, a portion of its light is blocked by the enormous red star, causing a subtle but measurable decrease in the system's total brightness. Conversely, when VV Cephei B moves in front of the supergiant, it can partially obscure regions of VV Cephei A's outer layers, producing another dip in brightness, though less pronounced due to the supergiant's sheer dominance in luminosity. These variations are not instantaneous. They develop gradually over months due to the immense size of VV Cephei A and the elliptical nature of the orbital path, creating prolonged periods of dimming that can be observed and recorded with careful photometry. The study of these eclipses, particularly the timing, depth, and duration, provides astronomers with a wealth of information. For example, the exact duration of the eclipse gives clues about the size of VV Cephei A's outer envelope. Because the star is not a solid object, but a diffuse, gaseous supergiant, the way light is blocked and gradually fades can also reveal the density and structure of its atmosphere. Observing successive eclipses over multiple decades allows scientists to measure the orbital period with precision, verify the eccentricity of the orbit, and even detect slight changes over time that could indicate mass transfer or atmospheric expansion in the red supergiant. In this way, the simple observation of periodic dimming becomes a powerful tool for understanding one of the largest stars in the universe. The eclipse phenomenon also highlights the enormous scale of VV Cephei A. Given the star's radius, over 1,000 times that of the Sun, the time it takes for VV Cephei B to traverse its disk is enormous. A single transit can last hundreds of days, making these eclipses some of the longest-lasting observed among binary stars. Unlike shorter-period binaries, where eclipses last hours or days, the VV Cephei system offers a slow-motion view of stellar interaction, allowing astronomers to study gradual changes in the red supergiant's atmosphere, the effects of tidal forces, and even subtle shifts in the orbital plane over time. This extended timescale is a direct consequence of the supergiant's immense size and the relatively wide separation between the stars in their elliptical orbit. Moreover, the eclipses serve as a natural laboratory for studying mass loss and stellar winds. VV Cephei A continuously sheds material into space, and the way this ejected gas interacts with the light of VV Cephei B during transits provides indirect information about the density, composition, and velocity of the expelled material. Spectroscopic observations during eclipses reveal absorption and emission features that trace the movement of gas and reveal complex patterns in the star's extended envelope. These insights are invaluable because they allow scientists to link surface phenomena to internal processes in a star that is otherwise too distant to examine directly. The historical discovery of VV Cephei as a binary system also relied heavily on these eclipses. Before the advent of high-resolution imaging and interferometry, astronomers noted the periodic dips in brightness and deduced the presence of a companion star. The fact that the system's light curve displayed a regular pattern over a 20.3-year cycle was one of the first indications that the red supergiant was not alone. This discovery exemplifies how careful observation of light, a simple signal traveling across thousands of light years, can unveil detailed information about objects far beyond direct reach, demonstrating the power of photometry and the ingenuity of astronomers working with limited observational tools.
In addition, the eclipses provide a dynamic view of the interaction between stars at vastly different scales. The relatively tiny but hot and massive VV Cephei B moves in the shadow of a star so enormous that its outer layers are effectively a turbulent ocean of gas. The eclipses allow astronomers to probe the edges of VV Cephei A's atmosphere, detecting irregularities, pulsations, and other phenomena that would otherwise remain hidden. By studying the precise timing and depth of each eclipse, scientists can construct detailed models of the star's shape, surface irregularities, and mass distribution. This makes the VV Cephei system not just an example of a large star with a companion, but a laboratory for understanding how binary interactions affect the evolution of massive stars. Finally, the eclipses emphasize the scale of time in astrophysics. Unlike everyday human experiences, where events unfold over seconds, minutes, or hours, the eclipse of VV Cephei B across its massive companion is a slow, deliberate cosmic dance that unfolds over years. Observing these long-duration eclipses requires patience, meticulous data collection, and intergenerational scientific collaboration. Each cycle provides astronomers with additional insights, gradually refining our understanding of the system and revealing subtleties that would be impossible to detect in a shorter period binary. The eclipses are thus both a dramatic visual phenomenon and a vital scientific tool, linking the movements of these distant stars to fundamental principles of physics, gravity, and stellar evolution. In essence, the periodic dimming of the VV Cephei system is much more than an observational curiosity. It revealed the binary nature of the system, allowed precise measurements of size and orbital parameters, offered insights into stellar winds and atmospheric structure, and provided a rare opportunity to study interactions between stars of drastically different scales. The eclipses turn light curves into a story, a slow unfolding narrative of cosmic proportions, giving astronomers a window into the life and dynamics of one of the universe's largest stars. Through these observations, we can witness the intricate ballet of two celestial giants, a dance that stretches over decades and encompasses unimaginable distances and energies. Astronomers rely on light curves, plots of a star's brightness over time, as one of the most powerful tools for studying VV Cephei A and its companion. A light curve is essentially a timeline of how much light reaches Earth from the system, capturing subtle fluctuations caused by eclipses, pulsations, or atmospheric changes. For VV Cephei A, these curves are particularly informative because of the star's immense size and complex interactions with VV Cephei B. Over years and even decades, careful monitoring of these brightness variations allows scientists to infer the physical characteristics of both stars and the geometry of their orbit, turning what might seem like simple dips in light into a detailed portrait of a distant stellar system. The orbital motion of the binary pair is reflected clearly in the light curves. As VV Cephei B passes in front of or behind VV Cephei A, the system's brightness decreases in a predictable pattern. By recording the precise timing and depth of these dips, astronomers can determine the orbital period of the companion, roughly 20.3 years, and measure the eccentricity and inclination of the orbit. The duration of each eclipse, which can last for hundreds of days due to the red supergiant's enormous radius, also provides critical information about VV Cephei A's size and the relative separation of the two stars. In essence, the light curve acts as a ruler, allowing scientists to measure distances and dimensions in a system far beyond our ability to directly resolve with telescopes. Beyond eclipses, the light curves of VV Cephei A reveal subtle variations caused by stellar pulsations and surface activity. Red supergiants like VV Cephei A are not static. Their outer layers expand and contract over time due to instabilities in the star's atmosphere and convection currents in its massive interior. These pulsations can create slight changes in brightness, typically on the order of a few %, but they carry significant information. By analyzing these oscillations, astronomers can infer the density, temperature, and dynamics of the outer layers, as well as the star's internal structure. In a sense, the light curve becomes a diagnostic tool, allowing scientists to listen to the star's rhythms and understand processes occurring on scales impossible to observe directly. Tracking these brightness variations over decades also helps reveal mass loss and irregularities in the star's atmosphere. VV Cephei A sheds enormous amounts of material through intense stellar winds, and the density and distribution of this ejected gas can affect the system's observed light. As clouds of stellar material pass between the star and Earth, they can scatter or absorb light, producing fluctuations that are superimposed on the primary periodic signals from eclipses and pulsations. By carefully modeling these effects, astronomers can estimate how much mass the star is losing, the velocity of the outflowing gas, and the composition of the material being expelled. These measurements are crucial for understanding the late-stage evolution of massive stars and predicting the future behavior of VV Cephei A. Light curves also allow astronomers to detect asymmetries and surface irregularities on VV Cephei A. Unlike smaller stars such as the Sun, whose surfaces appear relatively uniform, red supergiants have enormous convective cells and turbulent atmospheres. These features can produce localized bright and dark spots, which in turn create small but measurable fluctuations in brightness over time. Observing these variations, especially when combined with spectral analysis, enables scientists to map temperature differences, track convection patterns, and study dynamic changes in the star's outer layers. In effect, the light curve transforms from a simple graph into a window into the star's complex boiling surface. Modern observations employ both ground-based telescopes and space-based instruments to construct highly precise light curves. Ground-based observatories, equipped with photometers and spectrographs, track long-term brightness trends and eclipses, while space telescopes such as Hubble or infrared observatories can detect subtle changes in luminosity unaffected by Earth's atmosphere. Combining these datasets produces a comprehensive picture of the star's behavior across multiple wavelengths, from visible red light to infrared, revealing processes hidden from the naked eye. This multi-wavelength approach is especially important for VV Cephei A because its cooler temperature means much of its energy is radiated in infrared, where its extended atmosphere and circumstellar material are most visible. Additionally, light curves provide insight into the interaction between VV Cephei A and its companion. During eclipses, the star's light is partially blocked, but careful observation can reveal fine details about the density and extent of the supergiant's outer layers. The gravitational pull of VV Cephei B also induces tides in VV Cephei A, subtly distorting its shape and potentially altering the timing and depth of eclipses. By monitoring these small but significant changes in the light curve over multiple orbital cycles, astronomers can refine models of the binary system, quantify tidal effects, and gain a better understanding of how massive stars influence each other when in close proximity. Long-term light curve analysis also plays a critical role in constraining predictions about VV Cephei A's evolution. By observing how its brightness changes over decades, astronomers can detect gradual trends indicative of ongoing expansion, changes in mass loss rates, or other long-term instabilities. These patterns provide early warnings of potential pre-supernova activity, offering a rare opportunity to study a red supergiant approaching the final stages of its life.
Because massive stars evolve on timescales much shorter than lower mass stars, observing such variations in real time is extraordinarily valuable for astrophysics.
In summary, light curves are a window into the dynamic life of VV Cephei A. They capture eclipses that reveal orbital parameters, pulsations that trace internal physics, fluctuations caused by mass loss and atmospheric irregularities, and subtle signals from interactions with VV Cephei B. By systematically observing these variations over decades, astronomers can reconstruct the star's size, orbit, and surface activity with remarkable precision. Light curves turn photons traveling across 5,000 light-years into a detailed narrative, allowing us to study the rhythms and behaviors of a star so immense that its surface could engulf our entire solar system. VV Cephei A's extraordinary mass, which places it among the heaviest stars known, is a product of both the environment in which it formed and the fundamental processes that govern star formation in our galaxy. Unlike stars such as the Sun, which form in relatively moderate pockets of interstellar gas and dust, VV Cephei A began its life in a dense, massive molecular cloud, a stellar nursery rich in raw material. These clouds, composed primarily of hydrogen with traces of helium and heavier elements, are often cold and turbulent, allowing gravity to overcome thermal pressure in localized regions. In such a dense environment, a protostar can rapidly accrete gas and dust, amassing hundreds of times the material that forms an average star. VV Cephei A is the culmination of one of these rare extreme formation events, where an unusually large portion of the cloud collapsed into a single gravitational center, igniting nuclear fusion in a star that would become truly colossal.
The formation of such massive stars is inherently competitive. Within a molecular cloud, many protostars vie for the same pool of material, and the most massive ones tend to dominate, their stronger gravitational pull enabling them to capture gas more efficiently. VV Cephei A likely benefited from this process, sweeping up nearby matter and growing faster and larger than most of its stellar siblings. This rapid accumulation of mass leads to higher core pressures and temperatures, which in turn accelerate the onset of nuclear fusion. Massive stars burn hotter and faster in their cores than smaller stars, initiating complex nuclear processes at an earlier stage. This combination of environmental richness and gravitational dominance is what allows a star like VV Cephei A to reach a mass and size that dwarfs most other stars in the galaxy. The density and composition of the cloud from which VV Cephei A formed also influence its eventual mass. In regions with higher concentrations of hydrogen, the raw fuel for fusion, a protostar can sustain higher accretion rates, allowing it to grow more quickly and maintain a larger envelope of gas. The presence of heavier elements, metals in astronomical terms, affects opacity, radiation pressure, and cooling rates, all of which influence the final mass the star can achieve. In the case of VV Cephei A, conditions were exceptionally favorable. A dense, metal-rich environment allowed the protostar to accumulate tremendous amounts of matter while maintaining stability long enough to ignite and sustain nuclear fusion, producing the enormous red supergiant we observe today. Massive stars like VV Cephei A also face internal and external challenges during formation that smaller stars rarely encounter. Radiation pressure from the hot core pushes outward, opposing gravitational collapse, and in many cases prevents additional mass from being accreted. Only the most robust protostars in the densest regions of a molecular cloud can overcome this outward force. VV Cephei A's final mass indicates that it successfully balanced these competing forces, using its gravity to dominate the surrounding environment while withstanding the enormous radiation pressure generated by its intense core fusion. This delicate balance is one reason why stars of this scale are extremely rare. They require precise conditions, exceptional density, and significant luck within the chaotic environment of a molecular cloud. Another factor contributing to VV Cephei A's mass is accretion via surrounding disks and inflows during its early life. Like many stars, it likely formed with a circumstellar disk composed of gas and dust.
In the case of massive stars, these disks can be incredibly massive themselves, funneling material efficiently onto the protostar. The inflow is aided by gravitational instabilities and sometimes by interactions with nearby stellar objects, allowing the protostar to continue growing even in a turbulent stellar nursery. The combination of a massive accretion disk and the star's inherent gravitational pull would have ensured that VV Cephei A accumulated far more material than typical stars, setting the stage for its eventual expansion into a red supergiant.
Once nuclear fusion begins, the star's mass governs almost every aspect of its evolution. More massive stars develop harder cores, faster fusion rates, and stronger radiation pressure, which in turn accelerates their life cycles. VV Cephei A's extraordinary mass ensures that it burns through nuclear fuel much faster than a star like the Sun. While our Sun will enjoy a stable life of roughly 10 billion years, VV Cephei A's main sequence phase was far shorter, measured in only a few million years. The initial mass, accumulated during formation, dictates this rapid progression, leading inevitably to the dramatic supergiant stage, where the star's radius swells to thousands of times that of the Sun and its outer layers become tenuous and unstable. The extreme mass also has consequences for stellar wind and mass loss even before the star reaches the supergiant phase. More massive stars exert stronger gravitational pull and generate more energetic radiation, which can drive powerful stellar winds from the outer layers. These winds gradually strip material from the star throughout its life, shaping both the star's evolution and the surrounding interstellar medium. In VV Cephei A's case, the combination of immense size and strong radiation ensures that mass loss is a defining characteristic, altering the star's envelope, creating extended circumstellar material, and contributing to the future supernova remnant that will form when the star finally ends its life. Finally, the rarity of stars like VV Cephei A is directly tied to the difficulty of assembling such enormous masses. Only the most massive molecular clouds, with ideal densities, compositions, and low levels of disruptive turbulence, can give rise to stars of this scale. Even when such conditions exist, the star must survive the intense radiation pressure, internal instabilities, and dynamic interactions with neighboring protostars long enough to accumulate and retain the majority of the material. That VV Cephei A achieved this feat highlights not only its exceptional nature, but also the delicate balance required for the formation of cosmic giants. Each massive star is the product of extraordinary circumstances, a convergence of environmental richness, gravitational dominance, and early life resilience that allows it to grow far beyond the limits of ordinary stellar formation. In essence, VV Cephei A's staggering mass is a result of an intricate interplay between dense molecular clouds, high accretion rates, gravitational dominance, and resilience against internal and external pressures. These factors allowed it to gather far more material than average stars like the Sun and set the stage for its remarkable journey as a red supergiant. Its mass governs everything that follows: its immense size, luminosity, instability, and eventual fate as a supernova. By studying how stars like VV Cephei A form and grow, astronomers gain insight not only into the mechanisms that produce the universe's most massive objects, but also into the cosmic conditions required for stellar extremes to exist. VV Cephei A is in a phase of stellar evolution that few stars ever reach, a late stage characterized by its red supergiant status, when the star has exhausted the hydrogen fuel at its core and begun fusing heavier elements. For most stars, including our Sun, the life cycle begins with hydrogen fusion in the core, a staple process that can last billions of years. In massive stars like VV Cephei A, this main sequence phase is far shorter, measured in only a few million years, due to the enormous pressures and temperatures in their cores that accelerate nuclear fusion. Once hydrogen is depleted, the star faces a fundamental change. The outward thermal pressure that counteracts gravity weakens, causing the core to contract while the outer layers expand dramatically. This expansion produces the enormous diffuse envelope that defines a red supergiant, stretching the star's radius to over 1,000 times that of the Sun. During this red supergiant phase, the star begins using heavier elements in its core, starting with helium and progressing to carbon, oxygen, and potentially even heavier nuclei depending on the star's mass. Each successive fusion stage requires higher temperatures and occurs over increasingly shorter periods, which makes this phase both dynamic and unstable. Unlike hydrogen fusion, which is relatively stable, the fusion of heavier elements generates pulses and fluctuations in energy output, creating turbulence in the star's outer layers. These instabilities contribute to the convective motion and surface irregularities observed in VV Cephei A and are part of the reason red supergiants exhibit brightness variations and massive stellar winds. The star's enormous size and diffuse outer layers make it particularly sensitive to these changes, as even small variations in core fusion can ripple outward and produce visible effects across thousands of millions of kilometers. The late-stage life of a red supergiant is a race against time. As fusion progresses from helium to heavier elements, the core becomes increasingly compact and dense, while the outer layers swell even further, reducing surface gravity and facilitating the loss of material through intense stellar winds. VV Cephei A, due to its extreme size and mass, is shedding vast amounts of gas and dust into space, contributing to the enrichment of the interstellar medium with elements like carbon, oxygen, and nitrogen. These expelled materials will later play a critical role in forming new stars and planets, illustrating how massive stars like VV Cephei A act as both destroyers and creators within the cosmic cycle. The process of mass loss also influences the star's future evolution, potentially altering the timing, intensity, and dynamics of its eventual supernova explosion. Red supergiants like VV Cephei A are also marked by their dynamic and convective outer layers. The enormous radius of the star allows for giant convective cells, some spanning a significant fraction of the star's diameter, where hot plasma rises and cooler material sinks. These convective motions are more pronounced than in smaller stars because the outer layers are much less tightly bound by gravity. This convective turbulence contributes to the irregularities observed in the star's brightness and can even produce asymmetries in the envelope, leading to anisotropic mass loss. In extreme cases, these instabilities can trigger episodic ejections of matter, further emphasizing the violent and unpredictable nature of a star in this late stage. The structure of VV Cephei A at this stage is layered, reflecting the different elements being fused in shells surrounding the inert core. At the center lies the densest region, possibly fusing silicon into iron or heavier elements depending on the star's exact mass. Surrounding this core are shells where carbon, oxygen, and helium continue to undergo fusion. The outermost layers, mostly hydrogen and partially ionized gas, form the vast envelope that dominates the star's visual appearance. The combination of a dense, energetic core with an enormous, tenuous outer envelope produces a delicate balance that makes red supergiants both spectacularly large and highly unstable. Even small perturbations in energy generation or mass distribution can propagate outward, causing dramatic surface effects visible in light curves and spectroscopic measurements. The evolutionary trajectory of VV Cephei A also underscores the short-lived nature of the red supergiant phase. While the main sequence phase may last a few million years, the red supergiant stage is fleeting by comparison, typically enduring only a few 100,000 years. This brevity makes such stars rare and particularly valuable for study, as astronomers only have a limited window to observe them before they reach the catastrophic end of their life cycle. The combination of extreme size, mass loss, and complex internal fusion processes creates a star that is in constant flux, offering a live demonstration of stellar evolution on a scale and magnitude impossible to replicate in smaller stars like our Sun. Importantly, this late stage also sets the stage for VV Cephei A's dramatic ultimate fate. The fusion of heavier and heavier elements in the core increases the star's density and gravitational instability. Once iron begins to accumulate, energy production through fusion no longer yields a net outward pressure, leaving gravity unchecked. At this point, the star teeters on the edge of collapse, with the potential to explode as a supernova. In this context, VV Cephei A's current status as a red supergiant is a brief but intense chapter in its life story, a phase of swelling, mass loss, and surface turbulence that precedes one of the most energetic events in the universe.
Observationally, VV Cephei A's red supergiant status manifests in multiple ways. Its deep red color, low surface temperature of approximately 3500 K, immense radius and brightness fluctuations are all direct consequences of the evolutionary processes unfolding within. Spectroscopic studies reveal the layered fusion shells and the chemical composition of the outer atmosphere, confirming that the star has exhausted hydrogen and is actively processing heavier elements. Light curves, especially during eclipses with VV Cephei B, provide additional confirmation of its size, mass loss rate, and surface activity, painting a comprehensive picture of a star in the final chapters of its life cycle. In essence, VV Cephei A's life as a red supergiant is a story of both magnificence and fragility. It is a stage defined by enormous scale, extreme physical processes, and constant instability, a delicate balancing act between outward radiation, core fusion, gravity, and convective turbulence. Observing and studying this phase offers unparalleled insights into the life cycle of massive stars, revealing not only how they evolve, but also how they influence the cosmos through mass loss, chemical enrichment, and eventual supernova explosions. In every sense, VV Cephei A embodies the awe-inspiring extremes of stellar evolution, illustrating both the grandeur and transience of the universe's most massive stars. VV Cephei A, like other red supergiants, exists in a delicate and often violent balance, and one of the most striking consequences of its enormous size and advanced evolutionary stage is its instability, which manifests in the form of intense stellar winds. Unlike smaller stars, such as the Sun, whose solar wind is relatively gentle, a star of VV Cephei A's magnitude experiences massive outflows of gas and plasma from its outer layers. These winds are driven by a combination of radiation pressure, thermal motion in the extended atmosphere, and pulsational activity in the star's convective envelope. The result is a steady but massive shedding of material into surrounding space, a process that can strip the star of significant portions of its outer layers over relatively short cosmic timescales. This mass loss is a defining feature of red supergiants and plays a critical role in shaping both the star's future evolution and the environment around it. The sheer scale of VV Cephei A's stellar winds is difficult to overstate. With a radius over 1,000 times that of the Sun, the outer layers are weakly bound by gravity, making it easier for energetic photons and convective motions to propel gas outward. Estimates suggest that the star may lose material at rates of 10 to the minus 5 to 10 to the minus 4 solar masses per year, which over tens of thousands of years amounts to several times the mass of the Sun being expelled into the interstellar medium. This material contributes to the chemical enrichment of the galaxy, providing heavier elements like carbon, oxygen, and nitrogen that are essential for the formation of future stars, planets, and even the building blocks of life. The winds also shape the star's immediate environment, creating a complex and turbulent circumstellar envelope that can extend millions of kilometers from the star's surface. The instability driving these winds originates in part from the star's convective envelope. Giant convection cells rise and fall across VV Cephei A's immense surface, transporting energy from the core outward. These cells generate fluctuations in surface pressure and temperature, creating regions of the atmosphere that can be propelled outward into space. Pulsations of the star, expansions and contractions caused by variations in internal pressure, further enhance these outflows. The combination of convection, pulsation, and radiation pressure produces a dynamic and sometimes asymmetric mass loss, meaning that the expelled material is not evenly distributed around the star. Observations of other red supergiants, combined with theoretical models, suggest that this asymmetry can have significant consequences for the shape of the eventual supernova remnant. The interaction of VV Cephei A's stellar wind with its companion, VV Cephei B, adds another layer of complexity. The smaller, hotter star emits strong ultraviolet radiation that can ionize and heat portions of the supergiant's ejected material, shaping the circumstellar environment. Additionally, the gravitational influence of VV Cephei B can focus some of the stellar wind along certain directions, creating regions of enhanced density and an anisotropy. This interaction between the red supergiant's mass loss and its companion not only affects the current structure of the system, but may also influence the dynamics of the eventual supernova, potentially guiding the expelled material and affecting the fate of the companion star. The composition of the stellar winds from VV Cephei A also provides astronomers with crucial information about the star's internal processes. Spectroscopic analysis of the ejected material reveals the presence of heavy elements produced in the core and transported outward by convection. By studying these winds, scientists can trace the chemical evolution of massive stars and better understand the contribution of red supergiants to galactic enrichment. The winds carry signatures of the fusion processes occurring deep within the star, allowing researchers to infer details about the star's past, including which elements have been fused and in what quantities, despite the star being thousands of light years away. Another consequence of these massive outflows is envelope instability, which can lead to episodic mass ejections. Occasionally, red supergiants like VV Cephei A experience violent bursts where large chunks of their outer layers are expelled suddenly rather than gradually. These events may be triggered by pulsational instabilities, rotational effects, or interactions with the star's magnetic field. Such eruptions can create complex circumstellar structures, including shells, arcs, and clumps of gas and dust. Observations of these features provide insight into the variability of stellar winds and the unpredictable nature of mass loss in the most massive stars, offering a glimpse of the processes that precede the dramatic final stages of the star's life. Stellar winds also directly influence VV Cephei A's lifespan and evolutionary trajectory. As mass is lost, the star's gravity weakens at the surface, and its outer layers become increasingly tenuous. This gradual reduction in mass can slightly alter the star's fusion rates and internal structure, potentially influencing the timing and nature of the supernova you will eventually undergo. Moreover, the loss of mass changes the dynamics of the binary system, subtly affecting the orbit of VV Cephei B and altering the gravitational balance between the two stars. These interactions between mass loss and orbital mechanics illustrate the interconnectedness of the system, showing that stellar winds are not merely an atmospheric phenomenon, but a fundamental factor shaping the evolution of both stars. From an observational perspective, the evidence of these winds is captured through multiple techniques. Infrared and radio observations detect the dust and gas carried outward, while spectroscopic data in optical and ultraviolet bands reveal the velocity and composition of the outflows. Extended envelopes around VV Cephei A, sometimes visible as faint nebulae, trace the material lost over thousands of years, offering a historical record of the star's mass loss history. By combining these observations with theoretical models of stellar evolution, astronomers can estimate the total mass ejected and predict how this will influence the star's eventual demise. In summary, VV Cephei A's instability and stellar winds define much of its current behavior and influence its ultimate fate. The combination of extreme size, low surface gravity, convective turbulence, pulsation, and radiation pressure drive the massive and often asymmetric flow of gas and dust into space. This mass loss enriches the galaxy, shapes the immediate environment of the star, interacts with the companion, and ultimately sets the stage for the supernova that will mark the end of VV Cephei A's life. These winds are both a symptom and a driver of the instability inherent in the late stages of massive star evolution, illustrating the immense power and fragility of the universe's largest stars. The inevitable fate of VV Cephei A is as dramatic as its enormous size suggests. It is destined to end its life in a spectacular supernova explosion, a cataclysmic event that will outshine entire galaxies for weeks or months. Unlike smaller stars like the Sun, which conclude their lives quietly by shedding outer layers and leaving behind the white dwarf, massive stars such as VV Cephei A cannot sustain fusion indefinitely. As the star fuses heavier and heavier elements in its core, it eventually produces iron, which cannot yield energy through fusion. When the core becomes predominantly iron, the delicate balance between radiation pressure pushing outward and gravity pulling inward collapses, triggering a rapid and violent implosion. Within seconds, the core collapses to an incredibly dense state, producing a shockwave that propagates outward, blowing apart the outer layers in a supernova explosion of staggering energy. The exact outcome of the supernova will depend on VV Cephei A's final mass at the moment of collapse. If enough mass remains in the core after years of stellar wind-driven mass loss, the imploding core could exceed the Tolman-Oppenheimer-Volkoff limit, collapsing into a black hole, an object whose gravity is so intense that not even light can escape. Alternatively, if the core mass is slightly lower, the collapse may halt at the neutron degenerate state, resulting in a neutron star, an ultra-dense object roughly the size of a city but containing more mass than the Sun. Either scenario marks the end of VV Cephei A as a luminous visible star, but in each case the explosion will enrich the surrounding interstellar medium with newly forged heavy elements, sowing the seeds for future generations of stars, planets, and even life itself. Leading up to the supernova, VV Cephei A is already exhibiting signs of instability and intense mass loss, which are precursors to its eventual collapse. The outer layers, continually blown off by stellar winds and episodic eruptions, will interact with the eventual supernova shockwave, producing a highly structured and luminous remnant. These circumstellar shells of gas and dust, expelled over tens of thousands of years, will glow when energized by the explosive blast, creating a complex and beautiful nebula in the aftermath. In some cases, dense shells may even partially absorb or redirect the energy of the explosion, affecting the observed brightness and spectral characteristics of the supernova. The surrounding environment, shaped in part by decades or centuries of mass loss, ensures that VV Cephei A's final act will be both a violent explosion and an artistic display of cosmic architecture.
The timing of the supernova is uncertain, but will occur on astronomical timescales rather than human ones. Red supergiants like VV Cephei A may linger in this swollen, unstable state for a few 100,000 years, a blink of an eye in the universe, but far longer than any human lifespan. Observing the star now provides a rare glimpse into the prelude to one of the universe's most energetic events. Scientists are especially interested in stars like VV Cephei A because witnessing a supernova from a nearby red supergiant would allow astronomers to test models of stellar collapse, nucleosynthesis, and shockwave propagation in unprecedented detail. In essence, the star is living its final act slowly, offering a prolonged opportunity to understand the physics behind its ultimate explosion. The supernova explosion will also have profound implications for VV Cephei B, its blue companion. Depending on the distance between the two stars at the moment of collapse, the shockwave could strip the companion of outer layers or disrupt its orbit entirely. In the most extreme case, the explosion could unbind the binary system, sending VV Cephei B hurtling through space at high velocity. Even if the companion survives relatively unscathed, it will be bathed in intense radiation and debris, altering its atmosphere and potentially affecting its long-term evolution. The interconnectedness of the binary system ensures that VV Cephei A's death is not an isolated event, but one with immediate and lasting consequences for its neighbor. The supernova itself will be a source of both light and elements. During the explosion, heavier elements including iron, nickel, and even some heavier nuclei produced in the core and during the shockwave will be ejected at enormous speeds, sometimes exceeding 10,000 kilometers per second. These elements enrich the galaxy, providing raw material for planets, asteroids, and eventually life. The visual spectacle of a supernova is often accompanied by gamma rays, X-rays, and neutrino bursts, allowing astronomers to study extreme physics that cannot be reproduced in laboratories on Earth. For VV Cephei A, the supernova represents both a violent end and a lasting legacy in the cosmic ecosystem. Astronomers also speculate about the type of supernova VV Cephei A will produce. Given its mass, size, and stage of evolution, it is likely to generate a Type 2P or Type 2L supernova, characterized by hydrogen in the spectrum and a plateau or linear decline in brightness over time. These events differ from Type 1a supernovae, which arise from binary white dwarfs, because their core collapse supernovae, a direct consequence of the star's inability to sustain fusion. The extensive circumstellar material, generated by decades or centuries of mass loss, may modify the observed light curve and spectral features, creating unique signatures that astronomers will study to understand both the progenitor star
and the physics of the explosion itself. Finally, the supernova will leave a lasting imprint on VV Cephei A's local environment. The expelled material will shock and compress nearby interstellar gas, potentially triggering the formation of new stars in a process known as triggered star formation. Over tens of thousands of years, the remnant will evolve into a supernova remnant, a glowing nebula shaped by magnetic fields, radiation, and prior mass loss. In this way, the death of VV Cephei A, while violent and destructive on a stellar scale, contributes to the ongoing cycle of stellar birth and death, perpetuating the chemical evolution of the galaxy and ensuring that elements forged deep in the star's core become part of future generations of stars, planets, and life. In essence, the future of VV Cephei A as a supernova is both inevitable and profoundly consequential. It represents the culmination of millions of years of stellar evolution, the release of immense energy and material, and the creation of compact remnants such as neutron stars or black holes. Its death will be a violent, luminous, and transformative event that will affect its companion, reshape the surrounding space, and enrich the galaxy with heavy elements. VV Cephei A's life and death are a dramatic illustration of the universe's extremes, a testament to both the fragility and the power inherent in the most massive stars. The impending supernova of VV Cephei A will not occur in isolation. Its colossal companion, VV Cephei B, will inevitably experience the consequences of this stellar cataclysm. Although the blue star is considerably smaller and more compact than the gargantuan red supergiant, it lies close enough in their shared orbit that the supernova shockwave and ejected material could have dramatic effects. One of the most immediate risks to VV Cephei B is mass stripping. As the blast of material from VV Cephei A hurtles outward at speeds of tens of thousands of kilometers per second, the outer layers of the companion star could be partially stripped away. This would reduce its mass and potentially alter its surface composition, exposing hotter inner layers and leaving long-lasting scars on the star's atmosphere. Depending on the intensity and orientation of the explosion, the mass loss could be minor or severe, fundamentally reshaping VV Cephei B's structure.
The orbit of VV Cephei B is another factor that could be significantly affected by the supernova. Before the explosion, the two stars orbited each other with a period of roughly 20.3 years in an elliptical path. The sudden loss of mass from VV Cephei A's outer layers during the supernova will change the gravitational balance of the system almost instantaneously. In the most extreme scenario, the companion could be ejected from the binary system entirely, sent hurtling into interstellar space at high velocity. Alternatively, if it remains gravitationally bound, its orbit could become highly elliptical, with the distance from the supernova remnant varying dramatically from periastron to apastron. Either outcome represents a profound transformation of the system, showing how the life cycle of one star directly influences the trajectory and fate of its neighbor. Beyond structural and orbital effects, VV Cephei B could also experience intense radiation exposure from the supernova itself. Core collapse supernovae release enormous amounts of energy across the electromagnetic spectrum, from visible light to X-rays and gamma rays, accompanied by a flood of neutrinos. Even if VV Cephei B survives a physical shockwave, the radiation can heat its outer layers, temporarily increasing luminosity, ionizing atmospheric gases, and potentially triggering enhanced stellar wind or mass loss. This radiation bath may last for weeks to months as the supernova remnant expands, and could leave the companion star in a highly energized, unstable state, primed for subsequent atmospheric disturbances or episodic eruptions. The interaction between the companion and the supernova remnant may persist long after the initial explosion. As the ejected material expands outward, some of it could accrete onto VV Cephei B, adding mass and angular momentum to the star. This accretion might temporarily alter the rotation rate or surface dynamics, causing instabilities or even triggering bursts of activity in the star's atmosphere. In addition, the interaction could deposit heavy elements, iron, nickel, and other nuclei forged during the explosion onto the surface of VV Cephei B. Such enrichment would have long-term consequences for the star's spectral characteristics, chemical composition, and potentially its own future evolution. Astronomers studying other binary systems where one star has undergone a supernova provide insight into these processes. Observations of so-called runaway stars, massive companions flung at high velocities after a binary partner explodes, demonstrate that surviving stars often exhibit altered trajectories, high rotation rates, and unusual chemical signatures. VV Cephei B could experience similar phenomena, essentially becoming a living record of the supernova's energy and force. Over time, careful observation of its motion and composition would allow astronomers to reconstruct the dynamics of the explosion and the properties of VV Cephei A prior to its demise.
The potential impact of the supernova also emphasizes the interconnectedness of binary systems. While VV Cephei A dominates visually and gravitationally, VV Cephei B is far from a passive bystander. Its survival or transformation will be dictated by the mechanics of the explosion, the orientation and timing of the supernova, and the pre-existing orbit. In many ways, the fate of VV Cephei B underscores the idea that massive stars do not exist in isolation. Their births, lives, and deaths are profoundly influenced by the presence of companions, particularly in systems where mass and proximity magnify these interactions. Finally, VV Cephei B's response to the supernova could influence its long-term evolutionary path. Depending on how much mass it loses or gains, and how its orbit is altered, the star might evolve differently than it would have in isolation. It could eventually become a peculiar blue supergiant, or perhaps experience its own late-stage instability as a result of the altered conditions. In extreme cases, such interactions can even set the stage for another supernova or a compact object formation in the future, demonstrating that the death of one star can directly shape the fate of its companion and the surrounding stellar neighborhood. Stars like VV Cephei A are among the rarest objects in the galaxy, not only because of their immense size and mass, but also because of the short window of time during which they exist in this extreme state. The majority of stars in the universe are relatively small, low-mass stars like the Sun, which can maintain stable hydrogen fusion for billions of years. In contrast, massive stars capable of reaching red supergiant sizes, hundreds or thousands of times the Sun's radius, are born infrequently and live fleetingly on cosmic timescales. VV Cephei A, with its extraordinary mass and radius, represents an extreme outlier in stellar populations, a cosmic rarity that provides a unique glimpse into the processes governing the most massive and short-lived stars. The rarity of these stars stems from the precise and extreme conditions required for their formation. A star must form in an exceptionally dense molecular cloud with abundant hydrogen to accrete the enormous mass necessary to become a red supergiant. Even then, not all massive protostars survive long enough to reach the red supergiant stage. The intense radiation pressure, convective turbulence, and dynamic interactions with nearby stars can disrupt growth, eject mass, or even trigger premature collapse before the star achieves its final size. VV Cephei A's existence as a fully developed red supergiant is therefore not just remarkable, it is the result of an exceptionally favorable combination of circumstances that rarely occurs in the galaxy. Another factor that contributes to the rarity is the short-lived nature of the red supergiant phase. After exhausting hydrogen in their cores, massive stars expand rapidly and begin fusing heavier elements in successive shells. This phase lasts only a few 100,000 years, a blink of an eye compared to the millions or billions of years lower-mass stars spend on the main sequence. Because of this brevity, the probability of observing a red supergiant at any given moment is extremely low. Many stars pass through this phase unseen, and only a tiny fraction of massive stars in the galaxy are in this stage at any one time, making VV Cephei A a rare jewel in the stellar population. Observational challenges further amplify their scarcity in our catalogs. VV Cephei A is located roughly 5,000 light-years from Earth, meaning its light has traveled across vast stretches of space before reaching us. At such distances, even a star of immense luminosity can appear faint and difficult to resolve in detail. Additionally, Red supergiants are highly variable, with fluctuating brightness caused by pulsations, convective cells, and interactions with companions. This variability complicates measurements of size, mass, and luminosity, making accurate characterization challenging. The combination of distance, variability, and the rarity of massive progenitor stars means that few red supergiants are well studied, and even among these, VV Cephei A is among the most extreme and enigmatic. The binary nature of VV Cephei A adds both opportunities and complications to its study. On one hand, the presence of a companion like VV Cephei B provides a way to measure mass and orbital dynamics that would be nearly impossible for an isolated red supergiant. On the other hand, the gravitational and radiative interactions between the two stars introduce additional variables, such as eclipses, mass transfer, and perturbations in the envelope that make precise measurements more complex. Understanding VV Cephei A thus requires careful modeling, long-term observation, and sophisticated techniques that account for the interplay between size, variability, and companion-induced phenomena. Even among red supergiants that are relatively nearby and easier to observe, VV Cephei A stands out for its enormous size and mass, which place it at the upper extreme of known stellar dimensions. While stars like Betelgeuse and VY Canis Majoris have been well studied, VV Cephei A surpasses them in some estimates, making it a key object for studying the limits of stellar evolution. Its rarity and extreme nature provide a benchmark for testing theoretical models, particularly concerning the formation, mass loss, and ultimate fate of the universe's largest stars. Every observation of VV Cephei A contributes valuable data, helping refine our understanding of these ephemeral giants. The scarcity of stars like VV Cephei A also emphasizes the importance of multi-wavelength astronomy. To study such distant, massive, and variable stars, astronomers rely on a combination of visible light, infrared, and radio observations, along with spectroscopy and interferometry. Infrared observations are especially important because red supergiants emit much of their energy at longer wavelengths due to their cooler surface temperatures. These observations allow scientists to penetrate circumstellar dust, study stellar winds, and map extended atmospheres, revealing details about mass loss and structural instability that would be invisible in optical light alone. Without these techniques, even a star as massive and luminous as VV Cephei A could remain largely enigmatic. In short, red supergiants of VV Cephei A scale are extremely rare, fleeting, and difficult to study. Their formation requires exceptional conditions. Their existence in the red supergiant stage is brief on cosmic timescales, and their distance and variability make observational study challenging. Yet it is precisely this combination of rarity and extremity that makes VV Cephei A invaluable. As one of the universe's largest and most extreme stars, it provides a unique laboratory for understanding the life cycles, mass loss, and ultimate fates of massive stars, offering insights into the processes that shape galaxies and the cosmic ecosystem. Observing VV Cephei A is like peering into a rare and fleeting chapter in the life story of the universe, where the extremes of size, mass, and energy converge in a single, awe-inspiring object. Studying VV Cephei A offers astronomers an unparalleled window into the life cycles of the most massive stars in the universe, providing critical insights that smaller or more common stars cannot offer. Because of its extraordinary size, mass, and evolutionary stage, VV Cephei A serves as a natural laboratory for understanding phenomena that shape stellar evolution on extreme scales. Observations of this star allow scientists to examine how massive stars expand into red supergiants, how they lose mass over time, and how their interactions with companion stars influence their development. Every fluctuation in its brightness, every layer of ejected material, and every movement within its binary system yields data that informs theoretical models, helping bridge the gap between simulation and reality. By studying VV Cephei A, astronomers can refine predictions about the fate of other massive stars and the broader processes governing the evolution of galaxies. One of the primary lessons from VV Cephei A concerns mass loss and stellar winds. As a red supergiant, the star sheds material at extraordinary rates, producing dense circumstellar envelopes that influence both the star itself and the surrounding space. By observing the structure, velocity, and composition of this expelled material, astronomers can better understand how massive stars recycle matter into the galaxy, enriching it with heavy elements like carbon, oxygen, and nitrogen. These elements are critical for the formation of future stars, planets, and potentially life. VV Cephei A demonstrates that mass loss is not merely a peripheral process, but a central factor in the evolution of massive stars, affecting their internal structure, lifespan, and the conditions under which they eventually explode as supernova. The star's binary nature adds another layer of scientific insight. Observing the interactions between VV Cephei A and its smaller blue companion, VV Cephei B, provides valuable data on how massive stars influence one another. Eclipses, tidal interactions, and mass transfer events can be tracked through light curves and spectroscopic measurements, revealing how gravitational forces and radiation shape the structure of both stars. These observations help astronomers understand the broader dynamics of binary systems, which are surprisingly common among massive stars. The lessons learned from VV Cephei A can be applied to other binary systems across the galaxy, offering clues about stellar evolution in environments where stars cannot be studied in isolation. VV Cephei A also teaches astronomers about the internal physics of red supergiants, which are challenging to model due to their enormous size and complex convective envelopes. By tracking variations in brightness and analyzing spectral lines, scientists can infer details about surface activity, pulsations, and convection within the star. These insights are critical for understanding how energy generated in the core propagates outward, how instabilities develop in the outer layers, and how these factors contribute to mass loss and eventual supernova behavior. Observations of VV Cephei A provide rare empirical constraints that can validate or challenge theoretical models of massive star interiors, helping refine our understanding of the physics governing stellar evolution at the extreme upper end of the mass spectrum.
Another important lesson is related to the life cycle of massive stars and their eventual supernovae. VV Cephei A is approaching the end of its life, and by studying its size, luminosity, mass loss, and chemical composition, astronomers can better predict the timing and characteristics of its eventual explosion. Observations of similar stars in pre-supernova stages are extremely rare, so VV Cephei A offers a unique opportunity to link late-stage stellar evolution with supernova physics. Data gathered from this star can improve predictions about supernova brightness, shockwave dynamics, remnant formation, and the influence of a companion star, providing a template for understanding the death of other massive stars across the cosmos. The study of VV Cephei A also provides insight into circumstellar material and nebular formation. The star's intense stellar winds and episodic mass ejections create extended envelopes of gas and dust that can interact with the supernova blast when it occurs. By observing these envelopes, astronomers can investigate how massive stars shape their immediate environment before they explode. This helps explain the origin of complex nebulae and supernova remnants observed elsewhere in the galaxy, linking the life of a single massive star to broader galactic phenomena. VV Cephei A in effect demonstrates that the death of one star is a driver of ongoing cosmic evolution, shaping matter and conditions for generations of stars to come. VV Cephei A also provides comparative insights when studied alongside other extreme stars like Betelgeuse, VY Canis Majoris, or UY Scuti. By examining differences in size, luminosity, mass loss rates, and variability among these giants, astronomers can refine models of stellar evolution, better estimate stellar lifetimes, and understand the factors that determine a star's ultimate fate. VV Cephei A, with its immense size and binary dynamics, represents a crucial data point at the upper extreme of known red supergiants, offering a benchmark against which other massive stars can be measured. Its study enhances our understanding of the diversity and range of behaviors that massive stars exhibit. Finally, VV Cephei A illustrates the interconnectedness of astrophysical phenomena. Its mass, size, luminosity, variability, winds, and interactions with VV Cephei B are not isolated traits. They are linked through the physics of stellar evolution, nuclear fusion, gravity, and radiation. By carefully observing and modeling these interactions, astronomers can gain a holistic understanding of how massive stars live and die, how they affect their companions and surroundings, and how they contribute to the chemical and structural evolution of galaxies. VV Cephei A is thus more than an extraordinary individual star. It is a laboratory for understanding some of the most fundamental processes shaping the universe. In essence, VV Cephei A offers a unique educational opportunity for astrophysicists. It allows scientists to study the life cycle of extreme stars, understand mass loss and stellar winds, examine binary interactions, and gain insight into the precursors of supernovae. By unlocking the mysteries of VV Cephei A, astronomers can refine models of massive star evolution, predict the fate of similar stars, and understand how the elements necessary for planets and life are dispersed throughout the cosmos. The star is not just a distant beacon of light. It is a living archive of the physics, chemistry, and dynamics that govern the most massive stars in the universe, providing lessons that extend far beyond its immediate stellar neighborhood. Despite decades of observation and study, VV Cephei A continues to confound astronomers with uncertainties regarding its exact size and mass, a testament to the inherent difficulties in measuring stars of such extreme scale and complexity. Unlike smaller, more stable stars, red supergiants like VV Cephei A have vast, tenuous outer layers that are not sharply defined, making it challenging to determine a precise surface for measurement. Its radius is estimated to be anywhere from 1,000 to nearly 1,900 times that of the Sun, a massive range that reflects the limitations of current observational techniques and the complex, dynamic nature of the star's atmosphere. Even its total mass is uncertain, with estimates fluctuating between 15 and 40 solar masses, depending on the method used. These variations highlight how elusive precise characterization can be for such colossal, highly variable stars. One source of uncertainty lies in interferometric measurements. Astronomers use arrays of telescopes to combine light waves, effectively creating a virtual telescope with a much larger aperture capable of resolving distant stars. While this technique allows scientists to measure angular diameters with unprecedented precision, the results depend heavily on how the star's diffuse outer layers are modeled. VV Cephei A's atmosphere is extremely extended and not uniform. Convection cells, pulsations, and asymmetric mass ejections create a surface that is constantly changing. Consequently, two interferometric observations taken even a few months apart can yield slightly different radii, contributing to the broad range of size estimates. Spectroscopic methods also introduce uncertainties. By analyzing absorption and emission lines in the star's spectrum, astronomers can infer temperature, surface gravity, and indirectly estimate mass and radius. However, the dense and turbulent atmosphere of a red supergiant like VV Cephei A complicates these interpretations. The lines are often broadened or shifted by convective motion, pulsations, and stellar winds, making it difficult to extract a clean measurement. Furthermore, the presence of its companion, VV Cephei B, introduces additional spectral signatures that must be disentangled, creating the potential for systematic errors. The overlapping contributions from both stars in the binary system make spectroscopy a complex but essential tool, one that is prone to subtle ambiguities. Another challenge arises from the distance to the star, which affects almost every derived property. VV Cephei A is located roughly 5,000 light-years away, and even small uncertainties in distance translate into significant variations in calculated size and luminosity. For example, a 10% error in distance can lead to a comparable discrepancy in the estimated radius. Astronomers use parallax measurements, light curves, and standard candles to estimate distances. But at such extreme distances, the margin for error remains substantial. This distance uncertainty compounds the difficulty of precisely measuring a star whose atmosphere itself is diffuse and constantly changing.
The variable nature of the star further complicates matters. VV Cephei A exhibits changes in brightness due to pulsations, convection, and interactions with its companion. These variations affect not only photometric measurements, but also the inferred radius and temperature. A star that swells and contracts over time does not have a single well-defined size, and different observations may capture it at different phases of its pulsational cycle. Additionally, episodic mass loss events can temporarily extend the star's apparent atmosphere, creating even greater uncertainty in measurements of its outer boundary. Compounding all these factors is the challenge of model dependence. Astronomers rely on theoretical models of stellar atmospheres and interiors to interpret observational data. But these models are approximations, especially for extreme stars like VV Cephei A. Differences in assumed opacity, temperature gradients, or convective efficiency can yield significantly different predictions for radius and mass. Because red supergiants are at the upper extremes of stellar evolution, models that work well for smaller stars often require extrapolation, which introduces additional uncertainties. As a result, estimates derived from different models may vary widely even when based on similar observational data. The binary system dynamics also play a role in the uncertainty. VV Cephei A B's orbit provides one of the few ways to constrain the mass of VV Cephei A through the gravitational influence the supergiant exerts on its companion. However, the orbit is highly elongated, with eclipses that last for months, and the outer layers of VV Cephei A are so extended that they complicate calculations of the system's center of mass. Small errors in orbital parameters or assumptions about the envelope structure can lead to large variations in the inferred mass of the primary star. Finally, even among different observational teams and instruments, results often disagree, reflecting the combination of atmospheric complexity, pulsational variability, distance uncertainty, and model dependence. Some studies suggest VV Cephei A is closer to 1,000 solar radii, while others estimate nearly double that size. Similarly, mass estimates span a wide range, emphasizing that despite advances in technology and methodology, a complete understanding of the star's fundamental properties remains out of reach. These discrepancies keep VV Cephei A mysterious and captivating, fueling ongoing research and debate. In essence, the mystery of measurement uncertainty surrounding VV Cephei A is a direct consequence of its extreme physical characteristics and the challenges inherent in studying objects at the very limits of stellar evolution. Its enormous, variable, and diffuse outer layers, combined with distance, binary interactions, and model dependencies, ensure that astronomers must work with ranges and estimates rather than precise values. Yet it is precisely this uncertainty that makes VV Cephei A scientifically valuable. Each new observation and modeling effort contributes to refining our understanding of how the universe's largest stars live, interact, and die. The star's enigmatic nature continues to challenge astronomers, reminding us that even in the age of powerful telescopes and advanced physics, the universe still holds secrets that push the limits of human knowledge.
VV Cephei A stands as a monument to the extremes of the universe, a star so immense that it defies ordinary human comprehension, yet so ephemeral in the grand timeline of cosmic history. Its enormous size, tremendous mass, and violent activity are a reminder that the cosmos is not a static place. It is a dynamic, evolving arena in which forces of unimaginable scale shape and reshape matter across light years of space. From its birth in a dense molecular cloud to its impending death as a supernova, VV Cephei A embodies the cycle of creation and destruction that governs the universe. It sheds mass, influences its companion star, and injects elements into the interstellar medium, demonstrating that even individual stars play crucial roles in the chemical and structural evolution of galaxies. Observing VV Cephei A offers a humbling perspective on the relative scale and fleeting nature of life, both stellar and human. The star's radius is thousands of times larger than the Sun's. Its outer layers extend past the orbits of planets, and light itself takes hours to traverse from one side to the other. Yet, despite this grandeur, VV Cephei A exists for only a few 100,000 years in its red supergiant phase, a mere instant compared to the billions of years of smaller stars like the Sun. Its fleeting presence reminds us that even the mightiest objects in the cosmos are subject to the relentless passage of time, their luminous brilliance destined to fade, collapse, or explode. This juxtaposition of scale and impermanence lends a poignant beauty to the study of stars like VV Cephei A, making them both awe-inspiring and humbling. The star also emphasizes the complexity and interconnectedness of cosmic systems. Its massive size affects its companion star, VV Cephei B. Its violent winds shape the surrounding space, and its eventual supernova will redistribute matter across the galaxy. Observing these interactions gives astronomers insight not just into one star, but into the broader principles of astrophysics, from stellar evolution and mass transfer to supernova mechanics and galactic chemical enrichment. VV Cephei A is both a singular phenomenon and a piece of a larger cosmic puzzle, demonstrating how the extremes of individual stars can influence the universe at multiple scales. Moreover, VV Cephei A sparks a sense of wonder and curiosity that transcends scientific measurement. Its deep red hue, colossal size, and turbulent surface evoke images of a living, breathing cosmic entity, one whose existence pushes the limits of human imagination. Even with modern telescopes, sophisticated models, and decades of research, the star retains an aura of mystery, reminding us that the universe is far more complex and vast than our instruments and equations can fully capture. Each new observation brings incremental understanding, but the full story of VV Cephei A, its precise size, mass, and the exact moment of its supernova remains tantalizingly just out of reach. This blend of knowledge and mystery is a hallmark of astronomy, illustrating how science is a journey of discovery in an ever-expanding cosmos.
In a broader sense, the study of VV Cephei A also reflects the fragile balance between life and death in the universe. The star's immense energy output sustains its envelope against gravity, its nuclear fusion creates heavier elements, and its mass loss sculpts the environment around it. Yet all of these processes are temporary, culminating in a supernova that will obliterate the star as we know it. The briefness of this existence, despite its grandeur, mirrors the transient nature of phenomena across cosmic time. Galaxies collide, stars are born and die, and black holes form, all within the ever-moving tapestry of the universe. VV Cephei A exemplifies this delicate balance, highlighting both the power and the impermanence inherent in cosmic structures. Ultimately, VV Cephei A serves as a reminder of our place in the universe. While human lifespans are measured in decades, this star lives and evolves on scales of millions of years, dwarfing the solar system and altering space on enormous scales. Its companion star, its massive winds, and its future supernova illustrate the interdependence and dynamism of celestial bodies. Through the lens of VV Cephei A, we see not only the staggering magnitude of stellar physics, but also the fleeting, almost poetic nature of cosmic existence. The star's story is one of creation, transformation, and eventual destruction, a narrative that mirrors the cycles of matter and energy that govern the universe itself. VV Cephei A reminds us how vast and powerful the universe is, where even the mightiest star burns brightly for only a cosmic moment. Its presence inspires awe, curiosity, and a deep appreciation for the forces that shape the cosmos.
By studying this extraordinary star, astronomers gain not only knowledge about the life cycles of massive stars, but also a humbling perspective on the scale, beauty, and impermanence of the universe. In the grandeur of VV Cephei A, we witness both the majesty and the fragility of cosmic extremes, a luminous testament to the forces that govern everything from the tiniest atom to the largest star, and to the fleeting brilliance that characterizes the vast expanse of space. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.